So if you remember last lecture, we were talking about errors, and the error measure we liked was the relative approximate error. And we're going to use that eventually in pretty much every calculation we're doing to assess how our numerical method is doing, how well it's doing. One of the examples we worked with was computing an approximation to the derivative. We called that the forward Euler method, which was what you studied in high school, rise over run. And the distance, the run, we call that h, and we know from theory that the smaller the h and the limit as h goes to 0, we get an exact derivative. And we wanted to do a relative approximate error calculation for different values of h. And if you remember, the approximate error definition was, it was the difference, because we don't know the true value, we don't know the truth, we know we can get close to the truth. A good measure of error would be the difference between a better approximation or a more accurate approximation minus a less accurate approximation. So that means over these values of h, we can use the better approximation, which corresponds to a lower value of h, minus the approximation with the higher value of h. And we did that in code in class last time with a lot of, we did this brute force approach. Okay, so we did the brute force approach last time. I do not recommend it at all. And that brute force approach was equivalent to using Python as a calculator. Just do the derivative or the relative approximate error for each value of h. And I argued, like, yeah, this works, but it's like the worst thing you could do. What if I gave you 1,000 values of h or 5,000 values of h? You won't be doing that. And it's not effective. It's not efficient at all. And it's not using the facilities that Python provides you in order to be able to expand and do things at large scale. Okay. So we're going to do a better way by leveraging what we call vectorization in Python. So in Python, the benefit of working with NumPy arrays is that when you add 2 NumPy arrays, it's going to go and add each entry in the array for you, instead of having to do a for loop and loop over each entry and add each entry together. Same thing applies for multiplication, for division. In other words, basic operations on numbers are also valid on NumPy arrays. What that also means is that basic application of functions, like exponential, sine, cosine, etc., they work on numbers, but they also work on NumPy arrays. So if I take an entire NumPy array and apply an exponential to it, it's going to apply the exponential to each one of those values. And then, recognizing that, so I'll give you an example. Okay? Let's start by doing a better way. So we call this a better way, better approach. Okay? We will leverage vectorization, use NumPy vectorization features. So what vectorization means, it means it's just doing the operation element-wise for you without having you to do a for loop and applying it for each value. Okay? And I'm going to tie this directly to all of those values in the h, in the arrays of h. Okay? So if I were to create, for example, I'm going to give you an example first. Example. If I were to create let me get this a little bit up here. Okay. If I were to create a NumPy array, let's say np.array, put 1, 2, 3, 4, 5, okay, in it. And then I say np dot, and say result is equal NumPy dot exponential of x. What do you think is going to happen? When I call the exponential function on an array, what is it going to do? It's going to apply the exponential over each entry in the array. So is it going to return a number or an array? an array. What is the array going to contain? 1, e to the, exactly. So the first entry in the array will be e to the 1, second entry e to the 2, third entry e to the 3, and so on. Okay? That's gorgeous. Like in C++, you don't get that. Okay? So this is like really cool. So if I print when in doubt, what do? Print it out. Yes, thank you. Yeah, last year they were better. I would say when in doubt, they would go like, print it out, okay? So I want you to be better than last year's class, okay? So by the end, in a few weeks, I want you to be screaming it, okay? All right, so print result. If I print result, look, indeed, it is an array of the same size as that one. This one has 1, 2, 3, 4, 5 entries. This one has 1, 2, 3, 4, 5 entries. Each value you should trust is indeed, this is e to the 1. It's e is 2.718, right? This is e squared, e cubed, e to the 4th, and so on. This is very powerful, okay? So how can we now use this for our problem? Let me get the slides here. Move the slides here. Okay, so when I look at what we did previously, before we define the error, before we compute the error, we needed to compute the derivative approximation at each one of those values. Right? Now, those values are given to us already in what looks like an array. And if I can somehow apply this directly to this array, I would get all of those derivatives for the different values of h in one line. No? Let's try it. Okay? So my x value is fixed. X is equal, what? What was it? 0.3 or 3, whatever. Let's do 0.3. Doesn't matter. No. OK. H values is this guy. So I'm going to go ahead and just copy this from here. I'm going to make it a NumPy array. If you make it a list, it's not going to allow you to add them together. Because lists don't only contain numbers. They can contain strings and other variables, other types. Only on NumPy arrays you can do this, or SciPy type arrays, other like scientific computing things. But with NumPy, that's the standard. So I'm going to put NumPy array. I'm going to create an array of h values. Okay. So now you can make sure that, print h values. Yeah. Indeed, we got all of those values. Okay. Now I can compute my derivative approximations, and I will call that df values. Those are the approximations. Right? So what I'm going to do, I'm just going to put this formula. X is fixed. It's a single number, but h is an array. Do you think it's going to work if I put this formula and put h as an array in it? Let's try. Okay? I think it's going to work because I've done it before, but I trust Python. All right, so let's go ahead. And the best part is what I'm going to do. I'm going to steal this from here. Okay? I'm going to put it here. I'm going to clean it up a little bit. We got 0.5 times x plus h values now, minus 2 times np.exponential half x over h values. One line. So what do you think this is going to return to us? The only thing that's changing here are the h values. So this expression is going to take x. It's a single value, scalar, great. And then it's going to go over h values. It's going to go over each entry in h values, plug it in, and return another value. And that value is going to be what? The derivative at that h. And we're going to have as many values as there are h values. Okay? So let me print h values here. Print h values. Okay? Now print forward Euler, or df values. Just call it df vals. And we're going to do df values. Wow. One line. One line. Okay, 2 lines. But that's better than 1,000 lines above. So what's in these? What's here? What are these numbers? Come on, groups. What are those numbers? We're not going to go to the next step until someone tells me what those numbers are. Devin, you cannot raise your hand.
What's the
This is the last question you answer. I'm sorry. Yes. So, what do you think? What's in here?
It's just going to be the approximate value at
At which h value?
8.
At 8. So this array here, the df values, contains the derivative approximations at the different h values. The first one is going to correspond to the first h value. The second one is going to correspond to the second h value, and so on. Can we check that? Yeah, because we had that printed up in the previous one here. Okay? So if I print df at 8, df at 8 was 15.568. 15.568. Okay, let's print df4. Print df4. So that's df at h equal 4, if you remember. df4 was 3.7115. 3.7115. It's kind of magic, but it's really just kind of basic logical thinking. We're going to apply that expression element-wise to any array you put in there. Okay? You could put x as an array as well. That complicates things a little bit. If they're the same size, it's just going to take them at each entry and combine them together. Okay? Now this is great because now we have our df values. Okay? So now what do? We have the derivatives. Okay? We have the derivatives. The next step is to compute our relative approximate error. And the relative approximate error, I'm going to bring this down because I'm not that tall. Oh, this is much better. Okay? We're going to take the value at h equal 4 minus the value at h equal 8 divided by the value at h equal 4. Okay? That gives us the first relative approximate error between these two values here. And then the one at 2 minus the one at 4, the one at 1 minus the one at 2, and so on and so forth. In other words, we're going to take this minus this one, and then this minus this minus this minus that. Okay. We can do this with a for loop. We will loop over the df values, and we take the ones, I plus 1 minus I divided by the value at I plus 1 and define an error. Okay? I told you I really like lists and errors. I'm going to create an empty list. You just did the easy pie homework assignment. You saw we can create an empty list. I'm going to store the relative approximate errors in this list. So for each pair value of h, I'm going to compute an error, and I'm going to plug it in to append it to this empty list. Okay? But first, I need to also know the length of these values here. Okay? Because I'm going to loop over them. I'm going to go for I, for some counter going from 0 to the end. Okay? Do something. Okay. Now, I see this a lot. I'm going to come and say, oh, h contains 8 values or whatever, 7 values. 1, 2, 3, 4, 5, 6, 7, 8 values. And you'll be tempted to say n equal 8. Don't do that. N equal 8 is going to limit every amazing thing you've done so far and just make it only work for n equal 8. If h doesn't have n equal 8, it's not going to work. It will only work for 8 values. So why do that? Don't hard code anything that you don't need to. You can only hard code like constants, like gravitational constant or pi. Okay? But anything else, just keep it dynamic so that you can apply it to different conditions. Okay? So what we will do, instead of saying n equal 8, we're going to just grab the length of h values. Okay? So if you're in doubt, yes, thank you. Thank you. Okay. And I'm listening to who's contributing. Okay. Print n. It is 8. Indeed, 8. Sanity check. Okay, good. Best, simple, cheap debugging way. All right. So now let's do a for loop. In the easy pie, you saw a few different ways of doing for loops. You can loop over a range, or you can iterate h. We're going to do a range counter value, a range counter for loop right now. Okay? We're going to do for I. It's like I is so popular, the letter I. It's like the default counter. It's like funny, you know, why would you choose I as a counter like, instead of A or, you know, Q? Anyways, I, K, J, I, J, K. Just so happens I is I guess because it corresponds to the word index, you know, counter. Anyway, so we'll just keep it I. For I in range, so now I'm gonna need to loop. I need a range of indices to count so that I can access the value on df_vals. And what's going on in my mind now? I'm like, oh crap, how am I gonna do this? Okay, I need to access the entries in df_vals. I know df value 0 is gonna give me this, df values 1 is gonna give me that, and so on. So I need to be able to do df values 1 minus df values 0, df values 1, etc., right? So I need a counter. I need this counter, 0, 1, 2, 3. And I need it to go to as far as the end of the array. Okay? So we create that with a range. For I in range, and we're going to go from 0 to n minus 1. Why? Okay, let me print it first and see. Because when in doubt, you need to print it out. So print I. Okay. Okay, so now this range starts from 0, and it goes to 7. Actually, it goes to 6. Okay, it's going to 6, to an index of 6. Why? As I'm inside the loop, if I is 0, I'm going to do 1 minus 0, right? df values 1 minus df values 0, df values 2 minus df values 1, df values 3 minus df values 2, 4 minus 3, 5 minus 4, 6 minus 5, 7 minus 6. And inside the counter, I'm going to be doing I plus 1. So the maximum value I get for I is 6, because I need to access I plus 1, which is 7, which is the last value in the array. Okay? So that's how I'm thinking about it. If you're confused about that, run it until n, and it's going to crash. And they're like, oh, yeah, I should have run to n minus 1. Okay? And then you remember the logic, and you figure it out. OK, so let's see. We're going to say E is equal. That's a variable for error. We're going to do the I'm just going to copy this from here. Actually, no, I'm not going to copy that. mp dot, like self-plagiarizing. OK, so it's df values I plus 1 minus df values at I, okay, over df values at I plus 1, because I plus 1 contains the more accurate approximation. That's the lower value of h. And I contains the less accurate approximation. If I had given you h in reverse order, okay, you have to take that into consideration as well. Like which one is the more accurate would be I, the one that's more accurate. Just keep that in mind. Okay? More accurate minus less accurate. And this I plus 1 is the reason why I went to 6. Because at I equals 6, this is going to be 7, and that's actually the last index in the array. Yes?
So it's also to say for I in like df values or something like that?
But then you need to access the next h value. So you could do for h in h values, access that as an iterative thing. But then how do you access the next one? You need a counter. So you would do that. You would add a counter, but that adds more lines of code. So this is a little more succinct. Okay? Yeah. Okay. All right. And now I can do errors.append e. Right? So I'm now storing this temporary variable into errors. Now what happens, I don't have to declare different names for this. This is just a temporary dummy variable. It's a container to store a number. And then I'm going to take that number and append it here. It's going to make a copy of it and put it in errors. Okay? So let's see what happens. Oops. OK. So what do? Visualize it. Print errors. And look at that. It gave me the error. So we can multiply it by 100 to get a % error. Indeed. 319, 85. So if you go back here, we had 319, 85, 32, 14, right? Look at that, 319, 85, 32, 14. Now, this is scalable. Guys, this is scalable. I could put 100 values for h, it will just work. It will just work. No need to copy and paste this, okay, over and over again. Who's excited about this better approach? Like, you've probably seen it before, but if you haven't seen it, it's exciting, right? And when you think about it and dig into it, there's a lot that's going on behind the scenes. It's fun, okay? Okay. So, do you think we can do even better? Let me see. I'm going to move this dock and put it on the left. Okay. So let's see. Can we do better? Yeah. As I told you last time, there's going to be a better way. Okay? All right. Do you have an idea of how we can do this even better? Yes. Okay, so you're right, but here our objective is not to get to a derivative approximation that is below a certain value. Here we're just computing the error. So we're going to do this when we compute the Taylor series to approximate a number. But just here I'm talking about the mechanics of this. How could we do this in a way and avoid the for loop? Thanks. So that would simplify the interface, but you still have a for loop. Okay, is there a way to avoid the for loop? Sorry. No, so you still have a for loop. So the break is just going to break the for or while loop. Okay, so let me introduce you to, have you heard of array slicing? Anyone heard of array slicing? Yes, okay, I'll be the first to teach you about that. That's awesome. Okay. All right, so I'm going to introduce you to an incredible concept, also in Python, vectorization, that's called array slicing. And it allows us to arbitrarily index within an array and combine arrays together in very smart ways without even a single for loop or a while loop. It's a very powerful concept. Right? Let me introduce the idea first. If this is a NumPy array, let's call it A. It has some values in it. They are meaningless, okay? Don't ask me what these values are. These are just random numbers, okay? Those are not going to be on your exam, okay? So you don't have to memorize them, just for the sake of example, okay? So traditionally, we do forward indexing with Python arrays, right? We say A0 is 5.4, A at 1 is 7.2, A at 6 is 0.3, right? So we access and assign the array in that manner. Okay, so for example, A0, 5.4, A3, 21.2, whatever. Now, there's also something called a reverse index and access a Python array from the back. How do we do that? This is reverse indexing. If I say A minus 1, it's going to give me the last value. A minus 1 is going to give me. Why is this useful? You're going to see a lot of usefulness for it once we hit ODEs, but why is this useful just in general? Like, what if I tell you, give me the last item in an array? What would you do? Or you don't have to get the length of the, if I were to tell you, give me the last value in the array, first you have to figure out what the length of the array is, n equal length of the array, and then you have to index to that point. Here I can just go A minus 1 is going to give me 0.3. A minus 2 is going to give me 10.1, and so on. Very powerful. So think of Python arrays not as a line, think of them as a circle. Okay, you can go clockwise or counterclockwise, okay? Okay, that's pretty cool. All right, we haven't even started. Okay, so now that we know this kind of, now interestingly, on the reverse indexing, you start at minus 1, not at 0, because 0 is always for forward indexing, minus 1 is for reverse indexing, okay? Okay. You can also get subsets of an array, okay? We call those views. Essentially, you could say, what if I want only elements 1, 2, and 3 of an array? How can I get those? I just want to access those. Or what if I want 1, 3, and 5, just like every other entry in an array? NumPy has the facility to do that. We call this array slicing, okay? Some call them splicing, and I think it was just like a mistake. Someone said it's splicing. It's really array slicing. Slicing through the array like a, like a block of cheese, okay? All right. The basic syntax for array slicing looks like this, okay? Don't be terrified. It's very easy. We're going to use it a lot. Instead of just putting a and a single number to access one value, you could put a and give it a range. Okay? Start, stop. And what it returns a view, not a copy. So if you change the view, you're going to change the original array. But a window, okay, you're opening a little window into that array that contains the elements a start plus 1, all the way to stop minus 1. So it's like an open interval. So if I go a from 1 to 4, it will give me 7.2, 33, and 21.2. Okay? We're going to do examples together. Okay? Note that the element at the second index is not included in the view. It's like an open interval. Okay? So it's not. So when I index from 1 to 4, it will give me elements at 1, 2, and 3 only. So be mindful of that. So for example, a 0 to 2 will give me 5.4 and 7.2. When you're in doubt, create an array, slice through it, and then print it out. Okay? Because I always forget this. Okay? Okay. Also note that the view is not a copy, like I said. It is a reference. So any modification of the view will modify the original array. Okay. Now you can go all the way to the end. What if I want from 3 to the end or 2 to the end? To get to the end, you put nothing at the stop. Okay? You go from start to the end. It gives you everything. Here from element 3, which is 21.2, all the way to 0.3. You can also index in reverse. So 3 minus 1. Okay? Again, that is going to be an open interval. Okay? So it will not include 0.3. It will include 10.1. Again, if you're confused about this, create a new cell in your notebook. Type in a small array A, put 5 elements in it, and play around with that. Okay. Here's a summary of what this does. For array slicing, accessing an array start to stop. That's the standard way of approaching this. Items start at start and stop minus 1. That's the index. Start, semicolon, nothing. You go all the way to the end of the array. At nothing is going to give you element 0, so you don't have to put 0. If you ditch the 0, it gives you from the beginning of the array all the way to stop minus 1. And doing this gives you a copy of the whole array. So it doesn't do anything. Okay? Okay. So now we're going to repeat the previous activity. So this is slicing. Okay? How can we use slicing to redo our problem in a very efficient way? Show you a trick. Okay. So repeat the previous coding activity, but do it so that one can use an okay, Albert, that's not the one I want. Okay, never mind. So how can we use an array? Okay, how can we use slicing? Okay, to do this problem we were doing. We already did this. We had h values in a Python array and derivatives, df values. This is for different x, probably 5 or something. So that's why you see different numbers than your code. But suppose that these are the derivative values. You have an array. You have a bunch of values for h. Okay. Okay. And again, like I explained, this is the value at h equal 8. This is the value at h equal 0.25. And we did this in one shot, right? One line. Okay. Now, to compute the relative approximate error, we need to take the difference between consecutive entries in the derivatives array. So if you think about it, if you write it in this way, that's why it's so powerful to try to write things and try to visualize them. This was our derivative array. Our first error was defined by the difference between these two numbers, 14 minus 60, right? That's right. Better approximation minus worse approximation, better approximation. Same thing for this guy here, 7.7 minus 14, and so on, right? But that consists of if you think about it, the red arrows minus the green arrows. Red arrows minus the green arrows. Red arrows minus the green arrows. So what if we put the red arrows in an array and the green arrows in an array and take their difference? Wouldn't that work? And how can we create an array of red arrows? By slicing into the array. So think of it. We have the derivative values. It's got some big size in it. We need a subset of it starting from 1 to the end minus the subset starting from 0 to minus 1. That gives us the red values minus the green values. And bam, you compute your errors. No for loop. Isn't that brilliant? That is so cool. The people who designed Python are like geniuses, right? So this would be the array corresponding to the red arrows. This would be the array corresponding to the green arrows. We take their difference, divide by the array of the red arrows, and you're done. Okay? Let's do it. Okay? An even better approach using slicing. All right. So now, let's do this again. I already have, so we still need this. I'm just going to copy and paste this, just for the sake of being complete. All right, so h values, we just kind of keep them printed. Just copy and paste this. So we have our df values already. So those are our derivative values. Okay, our derivative values. Now, I want to take the subset of the red arrows minus the subset of the green arrows. Okay? So what I can do, if I do, so df, let's call them df, let's call them df high accuracy, df high. So those are the higher accuracy approximations. Okay, so df, the derivatives, high accuracy is going to be the subset of df values going from 0 to just the index before last. Okay, so it's going to be, so this would be the low. Okay, this would be the low. Okay, df low values, low accuracy approximations. Low accuracy approximation, we call them df low. So those are 60, 14, or whatever numbers we have. So it's going to be starting from this entry all the way to this one. It doesn't have to be 8 values. It could be 1,000 values. It doesn't matter. It's just going to work. It will just work. Okay? So let's see. Let's print it out. Bless you. df low. Indeed. Okay, I'm going to bring it down so I can reach. So the low approximations, or the green arrows, are going to be this, and this, right? And indeed, everything, that view, way to 1.19. Give us that subset, that view, that slice. Now the df high is going to be, df high is going to be the high accuracy ones, high accuracy approximations. Okay, df high is going to be df values, a view, a slice of that array. We're going to start from 1 all the way to the end. Because again, those are going to be the red arrows. So we're going to start from 1, index 1, all the way to the end. Agreed? Okay, good. All right. I'm glad when everybody agrees with me. df high. Okay, so now indeed, df high starts from 3.7, okay, all the way to 1.18. Now we can just take their difference. And guess what? This is an elementary operation on NumPy arrays. So you don't need a for loop. You just take df2 or df high minus df low or df high. And we'll just do it for you element-wise, okay? So errors equal df np.absolute df high minus df low. I need another parentheses here. Over df high. Okay, and then print errors. Errors df low. There you go. Times 100. Let's multiply by 100. All right, so now compare this to what we had before. Probably still typing. I'm just going to sneak peek here. 319, 85, 32, dot, 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 all the way to 1.58. Look at that. Same thing. No for loop, no length, etc. And I also guarantee you one thing. This will not show for small problems, but this will be over 50 times faster than the for loop that you will write. Every time. There's a reason for that beyond the scope of what we care about, but in a nutshell, Python does these operations in compiled code, not in interpreted code. So it's doing it at the machine level, and like in the processor, it's doing it really, really fast using optimization from C and C++ behind the scenes. Your for loop is not going to be as fast. Okay? And when you time this and over again, you can clock it. And with this, you get 100 times, 50 times, 100 times faster consistently. Is this going to show up for a problem with 1,000 values of h? Of course not. But once you hit problems that are of serious size for real analysis, you got 1 billion points you're looping over, this is going to make a big difference. The difference is going to be in hours of computational time. Okay? All right? Fun. Okay, who learned something today? Yeah, only some? Okay, good. Only a slice of the class. Okay. All right, so now I'm going to go back to a point that your colleague made today and your other colleague made last week, is about how about we put this derivative in a function, in a Python routine. So from now on, I want to distinguish the two words, function and routine. We can call Python function and mathematical function. Best I can, and correct me when I make a mistake, I will reserve the word function to a mathematical definition, like the exponential function, cosine function. It's a function. Anything Python, I'm going to call it a routine, Python routine. You can call it, we're defining a Python function, but I want to distinguish between the two. So anything we do in Python, we're going to call it a routine, and a mathematical function, the word function, we reserve it to a mathematical definition. So your colleague said, well, how about we create a routine or subroutine in Python that will accept any mathematical function to compute the approximate derivative. So that would be like the ultimate kind of upgrade of what you're doing here. Okay? So in other words, instead of having to do this np.exp 0.5x, etc., what if I told you do this over sine, cosine, log, cosine squared plus exponential, or like you're going to program all of those, right? So it becomes pretty ineffective. Okay, again, we're doing programming. Let's augment and elevate this. All right, so let's do it for any function now. For any function, Okay. So first, I'm going to define a derivative approximation routine. Define a derivative approximation routine. Routine, R-O-O. Wow. Yeah. Routine. I promise, when I came to America, I had better spelling ability, but I spent over the years here and start writing the way kind of things sound more than, because when you learn it as a foreign language, you follow the rules, etc. But then when you're immersed in the language, you're like, why can't I express it the way it sounds? Like, routine, like, what does that have? Anyway, so, all right, language. All right, so define a derivative approximation routine. So we will let's implement the forward Euler approximation, rise over run, for any function, Okay. So we do this by creating a definition, and you learn this in the Easy Pie. You might have seen it before. If not, this is your crash course in doing it right now. So we define a forward Euler approximation, okay? And every time you think about defining about a Python routine, this lecture turns out to be more important than I thought. It's like there's a cognitive awakening in Python. Actually, like the stuff we're covering here is what you need for the rest of the course. Okay, repeating the same. So how I think about Python routines, I think about them as a black box from the perspective of the user. And that black box takes one or more inputs, takes things, x values, tolerance, h values, whatever. Takes a bunch of things and produces something, or one or more things. Okay, so take inputs and outputs. That's how I like to think about them when I'm planning my implementation. I want to write a routine that computes the approximation to a derivative. What do I need? Let's look at the math. If you're in doubt, look at the math. Okay, let's look at the math. What does the forward Euler tell us? What do we need to compute this approximation? What do I need? Yes. X, h, and the mathematical function. Correct. Agreed? That's like the minimum number of items that we need to be able to compute the derivative. Okay? So here's what I'm going to do. I'm going to put those right here. F, X, and H. Okay. Now, if you've done any kind of programming before, you're like, okay, I accept this is a number and this is a number or an array. But here, putting F is like committing a sin in coding. Like, how could you are you passing a function? How do you pass a function to a routine? Well, Python allows you to do that. As long as F is another Python routine, or the name of another Python routine. So if I were to call forward Euler and I were to give it mp.exp, because mp.exp is another Python routine. What if I have a more complicated function, mp.exponential plus cosine plus log? I create another Python routine that implements that and pass it on to this one, and that's it. Like, seriously. So now we have one definition of the forward Euler that works for any function. So every time we're trying to approximate derivatives with this, we don't have to type everything. We just use this and define our mathematical function as its own Python routine once and reuse it. Okay. So let me finish with this first. Now, what's great, I love it when the code looks like my math, because then I can hold my code to the test. Like, do you look like my math? And if it looks like your math, you're more likely correct, unless your math is wrong, okay? Okay, so let's do this. Forward Euler is going to do f of x plus h minus f of x, okay? And we're going to divide it by h. All right. Now, a routine in Python, we defined the inputs, right? It did something. This is the black box, right? Now, because we are designing this, we know what's inside the black box. But now your routine needs to return something. What is it going to return? It should return this approximation, right? So what I like to do, again, this is my own practice. I always call it result so that I'm not ambiguous. Like, this is the result of my routine. No questions. And return the result. And all you have to do is say return result. OK, so let's test it. Forward Euler, OK, np.exp. np.exp, that's all you have to pass at, 0.3 and 0.125. Pep, it's returned a value, 1.437. Let's see if we computed that up here. So what did we have up here? We had x equals 0.3 and h 0.125. Okay, so it gave us 1.437, yeah. But that's not the function we dealt with before, okay? So that was only the exponential. Now, how can I implement this function, 2e to the 0.5x? I create another routine. Def my math function, okay? Okay, now my math function, it needs to take at least x. Because in this routine here, I'm calling f of something. If I were to pass my function to this guy, it's going to take my math function over here, it's going to put it here. It needs to be able to apply it to something. So I need an input for my function as well. And that's only going to be x. Okay? Simplest thing ever. Okay? Just x. And then I'm going to return 2.0 times np.exp minus 0.5 times x, right? So that was our mathematical function. Where is it, right? Yep, 2 to the 0.5, sorry, my mistake, okay? Okay, so now I can call it on, instead of np.exponential, I'll call it on my math function. Okay, and look at that, it gave 1.19, which was the value here, okay? Now this one here, we had to hard code, look at that. Every time we had to hard code it. But over here, I can just come up with any kind of arbitrary function. Def your function, right? Come up with a function. Give me a function. Come on, like exponential, log, cosine, whatever, right? np.exp, np.cosine x, okay? Okay, your function. It's going to give a value, okay? No need to hard. You write it cleanly. Because this routine is universal. To rewrite it every time, you have to approximate a different mathematical derivative for a different mathematical function. You write it once, and you define your mathematical functions here. Okay? I'll leave it at here today. Okay? So it's a very important lecture. I hope it's all recorded, no technical issues, right? I guarantee you, and you can ask Davin and Lillian, like 50% of what we're doing is what we covered. Slicing, for loops, and definition of routines, okay? We're going to do this over and over again. Master, please. Go repeat everything we did at home, on the bus, whatever, and come and ask us questions so you're ready for what's coming. What's going to come is going to be harder, but if you know this, then you don't have to worry about the coding. You can just worry about the theory. All right? Thank you. Have a great weekend.